Hello, everyone. Welcome back to our colloquium. And our speaker, our guest today is Shalom from the Institute for Advanced Study at Princeton. And he will tell us about structural theorems for the Host-Kra characteristic factors and inverse theorems for the Gowers uniformity norms.
Thank you. Thank you.
The stage is yours.
And thank you everyone for listening. So yeah, today I will tell you about joint work I'm pursuing with Asghar Germination and Terem Star. And as Ron said, it's about finding a correspondence between ergodic theoretical objects called the Host-Kra characteristic factors and some combinatorial objects called the Gowers uniformity norms, where our goal is to develop the theory that will eventually enable us to use tools from one area to prove problems or solve problems in other areas. So maybe before I begin, I would like to just give some applications for the Gowers uniformity norms in many areas without really going into details, just to show you how many there are. So there is a proof of Gowers where he introduced the Gowers norms, in which he proves quantitative bounds for Semeradi's theorem. I will tell you more about this in the next slide. Another application of the Gowers norms is a result of Green and Tau, where they prove that there exist infinitely many prime solutions to certain systems of linear equations. One example is this system of linear equations. They prove that it has infinitely many prime solutions. This is somehow interesting. So the main problem in this area is the twin prime conjecture, which is showing that this linear equation has infinitely many prime solutions. This is still open. So this is maybe a step towards proving twin prime conjecture. Another example is something called partition regularity. In this case, quadratic equations. So partition regularity is when whenever you decompose a set of natural numbers into finitely many sets, one of the sets contains a solution, in this case, x and y, which solve this equation. And the main problem in this area is the partition regularity of Pythagorean triplets, which is still an open problem. Another application of the Gowers norms, which is a bit different than the ones that we will talk about in this talk, but it's also an application that is interesting, and it's in computer science. It's about optimal testing of Reed-Muller codes. They're used in error correcting codes and stuff like that. There are applications in ergodic theory about convergence and limit behavior of multiple ergodic averages, and there are more applications. So as you can see, there are many applications for the Gowers norms in many areas of mathematics. So the first thing I would like to really tell you about is Semeradi's theorem and how ergodic theory and the Gowers norms in additive combinatorics were used to prove this result and how they are related. So Semeradi's theorem is a theorem in combinatorics, specifically additive combinatorics. It's a very famous result. And it says the following: if you have a subset of the natural numbers, which has positive upper Banach density, then it contains arbitrarily long arithmetic progressions. So the notion of density is defined like this, and the idea is to approximate a uniform probability measure on the natural numbers. What you do is to take an interval of length n, compute the probability that a random element in this interval belongs to E, and then take a limit or lim sup, because the limit may not always exist. This is the way of approximating uniform probability measure on the natural numbers. So I would like to tell you a bit about how one proves this theorem. There are many proofs. There are ergodic theoretical proofs by Fürstenberg. There is a harmonic analytic proof by Gowers. There are many other proofs, but I will focus on the two I mentioned previously. So the first thing I would like to do is to give you some intuition about sets of positive upper Banach density. So let's see some examples. So here's a very simple example of sets of positive density. If you take all the natural numbers, it has density 1 by definition, and it clearly satisfies Semeradi's theorem. This is a trivial example. Another trivial example is all arithmetic progressions of positive density. So If you look at the even numbers and odd numbers, they have density 1/2. And arithmetic progressions, of course, they satisfy Semiramis theorem. So let me give you one more example, which will be very important for this talk, and it's less trivial. So you can start by looking at the circle and fix some open subset of the circle U and some point x0, and then choose an irrational rotation alpha, and each second rotate the point x0 by alpha. Okay, so this will be alpha x0, and after 2 seconds, alpha 2x0, and so on. And then you let E be the set of all times where this orbit visits in U. And one can show that when alpha is irrational, this orbit is evenly distributed in the circle, which means that the density of E equals to the Lebesgue measure of U. So if U is half the circle, you would expect the orbit to spend half the time in this open subset. So whenever you take such open subset, you get a set of positive density because open subsets have positive Lebesgue measure. And here it's not as obvious as in the other two examples that Semiramis theorem holds. So I won't give you the details, but I will tell you what you should do. So in this case, what one can do is to take advantage of these underlying algebraic structure that we have here. So we have a compact abelian group, and the rotation on this compact abelian group, we have some underlying algebraic structure behind the definition of E. And on compact abelian groups, we have Fourier analysis. Any function on a compact abelian group is an infinite linear combination of characters. So what one can do is to look at the characteristic function of U and use this Fourier analysis to compute certain terms related to the existence of arithmetic progressions. And what I will try to define in this talk is the notion of structured sets. Structured sets are sets which has some underlying algebraic structure where methods like Fourier analysis or something called higher order Fourier analysis can be used to prove Semiramis theorem for these sets. But before I give you a formal definition of what a structured set is, let me give you an example of a set of positive density which has no algebraic structure. Okay, so if you want to construct a set which has no algebraic structure, the way to do it is to choose all the elements in the set uniformly at random. And the way to do it formally is to fix a sequence of countably many IID random variables. Each takes the value 1 in probability P and the value 0 in probability 1 minus P. And then let E be the set of all n for which xn is 1. So this is a random set and it depends on the values of the random variables. But using elementary probability theory, so the density of E by definition is the average of these random variables, the limit of the average. And by probability theory, it almost surely converges to the expectation, which is P. So another way of seeing this construction is just like you take a coin and you toss a coin infinitely many times, but you only write down the times where it lands on heads, for example. Then you will get a set of density 1/2 almost surely. So this is a way of getting sets of positive density. And here we take advantage of randomness to prove Semiramis theorem. So this time let's do it. So if you look at this intersection, this is a way of, so any element in this intersection is an indicator of a k+1 term arithmetic progression inside E, right? So if you have x in this intersection, then x plus n, x plus 2, and x plus kn is the k+1 term arithmetic progression in E. So if this is non-empty, we proved Semiramis theorem. So to show that it is non-empty, we can compute its density and show that the density is positive, which implies that it's actually infinite. There are infinitely many arithmetic progressions. And what you can do is the way to compute it is, again, to think about everything from the point of view of probability theory. So each one of these sets is an event. X is in E, x plus n is in E, and so on. Each one of them happen in probability P, and they're all independent by the construction. So we have here k+1 independent events. Each one of them happen in probability P. So they simultaneously happen in probability P to the k+1. Okay, so you can prove it by opening up the definitions, but that's the idea. And in particular, we see that we have Semerelli's theorem because of randomness. And we can also estimate the number, or actually the density of the arithmetic progressions. It's actually p to the k plus 1. And the idea behind many proofs of Semerelli's theorem is that when you take an arbitrary subset of the natural numbers, it's either pseudo-random, namely close to a random set in some precise sense, and therefore it satisfies Semerelli's theorem because of randomness. And if not, then this set is a non-generic set, and the reason is some algebraic structure. And then one can take advantage of the algebraic structure using, oh, did you hear me? Do you hear me?
Yes, we do.
Yes.
There was a slight interruption.
Okay, so yeah, the idea is either the set is very close to a random set, or it has some algebraic structure. And one of these reasons is why we have Semerelli's theorem. So the first one who noticed this dichotomy between randomness and structure was Furstenberg, where he gave an ergodic theoretical proof for Semerelli's theorem. And after that, Gowers had his own approach. And the approach of Gowers was a bit better because it allowed one to improve upon Furstenberg's approach. So let me jump straight to what Gowers did and how Gowers approached defining these notions of randomness and structure. So Gowers worked in the finitary settings. So instead of considering a subset of the natural numbers, Gowers worked with the finite group Z mod nz. And for Gowers, this n goes to infinity. So you're thinking about everything in the finitary settings, but now it's an infinite problem. It's a problem about all cyclic groups. And the idea is that when you have a subset of the natural numbers, then you can always take a very large interval and intersect the set with this very large interval and identify the very large interval with this finite group. And in general, Gowers defined norms which measure uniformity. He defined these norms originally on this group, the finite cyclic group, but one can define it in general for any finite abelian group. So let me tell you what Gowers defined. It's a bit technical, but it's actually quite interesting definition. So to define the Gowers norms, we start with a function on a finite abelian group. You can think about Z mod nz, and we make two definitions. So the first definition is the definition of a derivative, which you should think about as a multiplicative version of the discrete derivative. So the derivative in direction h is to change f in direction h and then multiply by the conjugate value. That's the definition of the derivative. And once we have the derivative, the UK Gowers norm of f is the average of all values of all k derivatives of f to some power. Now this seems quite technical, so let me explain why it makes sense. So let's see one example. What happens when you compute these norms when k equals to 2? So when k equals to 2, you will get this expression. And usually, we will apply these Gowers norms to very specific functions. So we will start with some subset of Z mod nz, and we will let f be the characteristic function of the set E. And if f is the characteristic function of the set E, this multiple is either 1 or 0. And if we average a quantity that is either 1 or 0, then we are counting. And the question is what we are counting. So when this product is 1, it's 1 exactly when x plus h1, x plus h2, x plus h1 plus h2, these elements are in E. And the reason why I draw it like this is that if you think about x and h1 and h2 as vectors, then this is a parallelepiped, a two-dimensional parallelepiped. So what the Gowers norms are doing, they are counting the average number of two-dimensional parallelepipeds inside the set E. And what the UK norms are doing is to count the average number of k-dimensional parallelepipeds inside E. And this was Gowers' way of measuring uniformity. You will start with a subset E, and you will count how many parallelepipeds it has. If it has roughly as many parallelepipeds as you would expect from a random set, you will say it is pseudo-random, and otherwise, it's not. So let me tell you exactly how Gowers' our strategy works. So Gowers strategy relies on an inequality, this inequality. So here on the left-hand side, we have the average number of arithmetic progressions. Here we are counting arithmetic progressions. And we can even take different functions. This is less or equal than the average number of parallel pipettes. To prove this inequality, one uses Cauchy-Schwarz inequality multiple times. And once you have this equality, this is the strategy. You start with an infinite subset of the natural numbers, which has positive density, delta. Then you fix n sufficiently large so that the size of this set is roughly delta times n. Right? This is exactly the definition. You can always do that. And then, so this size is roughly delta n. And so once I subtract delta, I get a function with 0 average. So this, we normalize the function f. And now comes something a bit counterintuitive. If the uniformity norm of f is small, namely it's a quantity converges to 0 as n goes to infinity, that's actually an indication of a lot of uniformity. If you want, you can think about it as this set is close in uniformity to delta. So what we get, if this is small, converges to 0 as n goes to infinity, then the average number of arithmetic progressions in our set, which is that if you plug in the characteristic function instead of all of these functions, it converges to what you get if you plug in just delta instead of all of these functions, which is delta to the k plus 1. So if the uniformity norm is small, then the number of arithmetic progressions is roughly as much as you would expect from a random set. Okay, so if it's small, we have a lot of arithmetic progressions. And if not, then this is the main question. So if we want to prove seminorms theorem, we start with a subset. Either it's pseudo-random and we win, or there needs to be some structure. So what can be said about functions which have large Gowers norm, where here large means greater than any quantity that doesn't go to 0 as n goes to infinity. So even if it's greater than 0.01, for us, it's going to be large. So we want to show that if it's large, there is some structure. And here are some instances where it's where we can do it. So again, you can think about G as Z mod NZ, but this works in general. And the inverse U1 is trivial. So the inverse U1 says that if a function f has a U1 norm greater than some constant delta that is independent on G, so you can think about G as Z mod NZ, and delta is independent on N, then then we say that f correlates with the constant 1. So here the inner product is defined on L2 of G, where mu is the normalized counting measure on G. G is a finite group, Z mod NZ, for example. So mu is just the normalized counting measure on G. So this inner product is just the average of f. So, but the way we read this statement is if f has large U1 norm, then f correlates with the constant. And the proof is trivial because these two quantities are actually equal. The inverse U2 is more sophisticated. So the inverse U2 is that if you have a large U2, so you have an abnormal number of two-dimensional parallel pipettes, then you have some structure. And the structure is that there exists a character, an algebraic function, so that f correlates with this character. The proof uses Fourier analysis, and the way we read it is as if f has large U2 norm, then f has large Fourier coefficient, and that's the structure.
So these claims are all for each specific G. They are not asymptotic, right?
No, so they are for all G simultaneously. So the idea is the delta is independent on G, right. And then whatever G you take, whatever F you take.
It's not for large enough G or anything, for any G.
I think you can do it, if you do it for large enough G, you can get it for any G because there will be only finitely many, and then, yeah, so, and in general, we only have some partial results. So the first one I would like to tell you is the one that Gowers used. So Gowers specifically studied the cyclic group. And he showed that if you have large Gowers norm, then at least locally, that is, you can identify a large arithmetic progression in this group Z mod NZ, so that if you compute the inner product only on this large arithmetic progression, you can show that f correlates with a function that we call a polynomial. Where here a polynomial function, here we take advantage of the fact that we have derivatives, so we can define a polynomial function as a function as a polynomial of degree k if all k plus 1 derivatives kills it. And these functions look, so polynomials of degree 0 are constants, polynomials of degree 1 are characters, and in general, they look like e to the 2 pi I and some polynomial. Okay. And I just want to say that what Gowers proved is actually, it makes sense. So if you go back to the definition, the Gowers norms are defined as the average over all derivatives of f. So if a function f is a polynomial, these derivatives are 1. And so the average is 1. And 1 is a constant that doesn't go to 0 as g or n goes to infinity. So polynomials are obvious obstruction to uniformity. And Gowers showed that locally, at least in the cyclic case, locally polynomials are the only obstruction to uniformity. Oh, sorry. And in this way, Gowers proved semi-additive theorem. So this was about Gowers proof and the finitary settings. And now I want to tell you about ergodic theory, and I will try to relate it to the Gowers norms as much as possible. So ergodic theory goes back to the infinitary world. So if Gowers studied finite groups, in ergodic theory, we will study countable abelian groups, but you can think about Z. And then in ergodic theory, we study dynamical systems like the irrational rotation that we discussed in the beginning. So a gamma system in general is a probability space. For instance, it could be the circle, the Borel sigma algebra on the circle, and the Haar measure on the circle, the back measure. And this is equipped with an action of gamma by measure preserving transformations like an irrational rotation. Okay, so in practice, for every gamma, we have a map T gamma from X to X, which preserves the measure. So in the irrational rotation, T to the N acts like alpha to the N, multiplication by alpha to the N. And then we have a quite technical definition that seems complicated, but it's actually not that much. So Host-Kra, not originally, but eventually defined some infinite versions or ergodic theoretical versions for the Gowers norms. So in the Gowers norms, we estimated the number of parallel pipettes. So here we do the same, but the parallel pipettes will be a bit different. So our parallel pipettes will look like X, TH1X, TH2X, TH1 plus H2X. Okay, so we choose the parallel pipettes according to the group action. And so we will define the derivative according to the group action. So H acts on X. So if I have a function on X, I can define the derivative in direction H using the same definition essentially as Gowers did. And then we need to average over all values of all of these derivatives. So to average over X is not a problem. X is a probability space, so we can take an integral. But averaging over the times, it's a bit complicated because unlike in the case of Gowers norms, now the group is countable, it's infinite. So we need to average over an infinite group. And the way to do it is to take Fellner sequences. So in the case, if you think about Z, then a Fellner sequence would be interval for minus n to n, for example. So you just average over the times from minus n to n, and then you take n to infinity. And it's not obvious that the limit exists, but it does. So basically, Host-Kra found a way to define the Gowers norms, an infinite version of the Gowers norms in ergodic theory. That's the point of this slide. And now I want to tell you how, so now we can ask the same question. So if a function is uniform, that's great. And what happens if a function has large seminorm? So I want to tell you how Host-Kra approached this infinite Gowers problem. So to do it, they use the notion that we use in ergodic theory, which we call factors. So dynamical systems they form a category. We have objects, which are dynamical systems, and we have maps. So a map from a dynamical system X to a dynamical system Y is a map from the set associated with X to the set associated with Y, which is measurable. And it pushes the measure, it maps the measure on X to the measure on Y, and it maps the T action to the S action. Now, you don't have to understand this definition. What I really need is this property. So when you have such a map and you have a function on Y, you can always lift it to a function on x. So we have an embedding of L to y in L to x, and the idea is that this is an isometric embedding. This is this definition. And so when I say a factor, in practice I mean that I distinguish a certain subset of functions on x, which I call special functions associated with y. Okay, so a factor is just a special subset of functions on x. And when I have this embedding of Hilbert spaces, I also have a map in the other direction. I have a projection from the big Hilbert space to the small Hilbert space. And this projection is called the conditional expectation. It's a bit better than an arbitrary projection because it comes from a factor map, but you should think about it as an orthogonal projection. Okay, so when I say a factor, I just say that I distinguish a certain family of functions. I hear someone talking, but...
Yes, just a small question. You call them seminorms because they may be 0 for non-zero f's?
Yeah, they even usually are 0 unless we are in very specific cases. So the 0 case is the uniform case here because this is the infinite version. So in the finite version, to be uniform is to be a quantity which goes to 0 as n goes to infinity. But now we are in the infinite version, so to be 0 is to be uniform. If you have a uniform measure 0, then you are uniform. And yeah, so we talked about these factors, and Host-Kra proved that for every k, you can find an increasing sequence of factors, so more and more and more special functions. And those functions determine uniformity completely. So if you have a bounded function, it's absolutely uniform, 100% uniform, if and only if it's orthogonal to the special functions coming from zkx. So in other words, these zkx, the special functions coming from zkx, are the structured functions, right? So if you're orthogonal to these functions, you are absolutely uniform. Or in other words, any function can be decomposed to its projection onto the structured functions, so a structured part, and an orthogonal part, which is absolutely uniform. So any function decomposes to a structured part and a uniform part. And then the main difficulty is to understand those structures. So we have structured components, but how they look like. So in some cases, it's easy to see what happens. And I will say that we have an underlying assumption that our systems are ergodic. This is a technical assumption that one can always assume. But assuming it, it's not too difficult to compute these structures. So the first the 0th, if you want, structure is just a single point. If you have a function on a single point, so these are just the constant functions. And this result says that if f has a large U1 seminorm, then it correlates with the constant, just like the inverse U1. So this is trivial. The second one is more sophisticated, and it uses spectral theory. And it's called the Kronecker factor. The functions on Z1x are the eigenfunctions on x, but also Z1x has some geometric structure. So Z1x is the maximal factor of x, isomorphic to a rotation on a compact abelian group, like the irrational rotation that we had in the beginning. So those are functions to which you can apply Fourier analysis. And in general, there is some higher order version of structured systems to which you will have to use some higher order version of Fourier analysis. And these we actually know only in the case where the acting group is Z. So when the acting group is Z, Host-Kra proved that the k factor is an inverse limit. So we have a category, so we can define inverse limits, but for us, it means that we can approximate the structured functions by even simpler functions. And the simpler functions are coming from some higher order of irrational rotation, which we call a k-step nil system. And on these higher order irrational rotations, we have other tools to deal with these actions. So these are many definitions. So let me give you one example that will explain how a higher order irrational rotation looks like. So this example of a higher order irrational rotation is called the Heisenberg system. So for any commutative ring R, you can look at the group of matrices over this commutative ring. So one on the diagonal and the elements from the ring. If R is commutative, then this group is two-step nilpotent. If you compute the commutator, these two become 0. Compute another commutator, this becomes 0. And then you can look at the space X, which is this quotient space. And this is called a two-step nil manifold. So nil is for nilpotent because the groups are nilpotent, and manifold because topologically it's a manifold. It's a locally Euclidean space. The Heisenberg group over R is locally a three-dimensional Euclidean space. The Heisenberg group over Z is discrete in the Heisenberg group over R, so this quotient is locally the three-dimensional Euclidean space. And also one can show that this quotient is compact. Now, when you have a quotient of two Lie groups, which is compact, you can equip it with the Borel sigma algebra and a probability measure which is invariant to this action. So you get a probability space. And to turn this probability space to a nil system or some higher order version of irrational rotation, you need to define an action. So in this case, let's define a Z action. So just one action and all of its powers. So you just choose any matrix you want. But if you want to get a non-trivial higher order version of irrational rotation, then the simplest way to do it is to choose this matrix where alpha and beta are irrational and independent over Q. And instead of this zero, you can take whatever you want, but this is the simplest example. So this is a version of a higher order version of irrational rotation, and it has 100% structure. And so again, I remind you that when we have a subset of an irrational rotation, we can use it to create subsets of positive density that satisfies Seminorms theorem. And I told you that when you work with an irrational rotation, you can take advantage of Fourier analysis because you have a compact abelian group. But here we don't have a compact abelian group. We have this nil manifold. So the question is, how can one still define Fourier analysis on nil manifolds? So what does it mean to have Fourier analysis? It means that I need to locate an orthonormal basis so that the algebra generated by this orthonormal basis it's dense, so say it's separating points. So I can start to define some functions. I can look at e to the 2 pi I a and all of its powers. And I can look at e to the 2 pi I b and all of its powers. And they are orthonormal to each other, and these two generate all functions which are independent on this C. But the problem is that when I want to look at the third function, the function e to the 2 pi ic, I have a problem because this is not a function on the quotient space. So these two are defined on the quotient space. If you multiply by an integer matrix, you get the same value. But this one is not. If you multiply by an integer matrix, you will get different values. So the real question, so in order to use higher order Fourier analysis, I need to somehow be able to speak about the C coordinate. But there is a way to do it. And the way to do it is to change it a bit. So instead of looking at e to the 2 pi iz, you look at e to the 2 pi iz minus the fractional part of x times y. And when you subtract this thing, you get a function that is well defined on the quotient. So once you have this and e of x, e of y, and all of their powers, you get an algebra which separates points, so it's dense, and they are all pairwise orthonormal, so you get some higher order Fourier analysis. And the reason I'm telling you this is that, so I remind you that when you have a subset of a dynamical system, it gives you a subset of natural numbers which has positive density. So if you have a function on a dynamical system, it gives you a sequence. So if I apply the orbit to this function, I get a very interesting sequence, which we call a bracket polynomial. The reason we call it a bracket polynomial is that, so n choose 2 is n squared minus n divided by 2. So it's a polynomial of degree 2 in n. And n alpha and beta, if you forget about the brackets, it's also a polynomial of degree 2. And with the brackets, it's a bracket polynomial. Here's a bracket polynomial is a polynomial with this fractional part. And the reason I'm telling you about this is that apparently, I told you about Gowers' work, and Gowers showed that locally obstructions to uniformity are polynomials. So it turns out that globally, at least in the cyclic case, obstruction to uniformity are these bracket polynomials. So somehow results from the infinitary world indicates what happens in the finitary world. So this was the history behind it. So shortly after Host-Kra work, Green and Tao published their paper about linear equations of primes. I told you about it in the beginning. And they show that under two conjectures, there are infinitely many, and they even compute asymptotics of prime solutions to linear equations. Now, one of the conjectures was that if a function f on the cyclic group has large Gowers norm, then it correlates with a nil sequence, where a nil sequence is a sequence like this, but with f being continuous. In our case, f is piecewise continuous. So they're not exactly the same, but practically they are the same. So large correlation with a nil sequence implies large correlation with bracket polynomial. Large correlation with bracket polynomial implies large correlation with a nil sequence. So they're essentially the same. So Green and Tau conjecture that what we see in the infinitary world, we should also see in the finitary world. And eventually they also proved it. And what was very interesting is that even so they proved it, we still don't understand how they are related. So Host-Kra theory about the nil systems, it uses ergodic theory, functional analysis. It's called soft analysis proof. But this result, it uses harmonic analysis or things that are we usually call them hard analysis. So we have completely different proofs that give very, very similar results. And even today, we don't know how to use a Host-Kra theory as a black box in order to prove these combinatorial results. But I will tell you about a new way we developed in order to prove this theorem using ergodic theory. So at this point, we only know that the results are very much the same, but the proofs are very, very different. And I would like to give you another example where we have some results in the infinitary world, which are very similar to the results in the finitary world, but we still don't understand exactly how. So just one more example, and then I will talk about new results. So the next thing I would like to tell you about is the case of vector spaces over finite fields. So if previously we talked about Z mod NZ, so now we will talk about Fp to the n. So Fp is the field with p elements, Z mod Pz. And we think about p as fixed and n goes to infinity. And before I begin, let me just say that once we have derivatives, we can define polynomials. So we can also define polynomials dynamically. So if I have a system, a function on the system is a polynomial if all k plus 1 derivatives kills it. And as usual, polynomials are obvious abstraction to, in this case, infinite uniformity. And Bergerson, Tau, and Ziegler, they try to study the infinite version of this problem. So if the infinite version of Z mod NZ is Z, they guessed that the infinite version of Fp is the countable dimensional vector space over Fp. So this is just a infinite direct sum of Fp. And an Fp omega system means that you have countably many transformations. All of them commute, and each one of them has each one of them is of order p. If you apply it p times, it dies. In this case, you can again define the Gowers norms. And here they found some interesting results. So instead of giving it the structure of inverse limit of nil systems, they gave a different structure. They actually have two structures. One is very good, but it assumes something called high characteristic. So the prime must be greater than the uniformity. And so this is only finitely many cases. But on those finitely many cases, you can show that the special functions can be approximated by those polynomial functions. So those polynomial functions are abstraction to uniformity. So this is really interesting because they show that globally, the obvious abstractions are the only abstractions. So this is a very strong result. But somehow, in general characteristic, they got a weaker result. So still, you don't have to consider those weird bracket polynomials. You still have to consider, but their degree might be higher. And they didn't manage to compute the optimal constant. They actually guessed that the optimal constant should be k, but they couldn't prove it. And still, what happens in the finitary setting? So again, in the finitary setting, we will see that polynomials, so we don't need nil sequences or bracket polynomials anymore. Polynomials will be abstraction to uniformity. And it was a surprise, for some reason it doesn't. Oh. And it was very surprising that here, there is no distinction of characteristics. So for any characteristic P, if you take a finite dimensional vector space over Fp, For every delta, there exists epsilon, so that if you have a bounded function which has large Gowers norm, you can find a polynomial of degree k with large correlation. And there is no assumption on the characteristic. You always get polynomial of the right degree. And nowadays we have multiple different proofs and even some quantitative ways of how epsilon depends on delta. But because of this result, it was very natural to conjecture that the constant ck here must also be k, because this is what we see in the finitary world. And somehow we guess that they should talk to each other. And for a lot of time, people really thought that it's obviously should be k, but we proved otherwise. So the first result I would like to tell you is that we have disproved this conjecture. It turns out that this ck may be larger than k, and specifically, if you consider the characteristic 2, f2 omega, then you can find a system X whose fifth Host-Kra factor is, it cannot be, it's the functions on this factor cannot be approximated by polynomials of degree 5. So this means that when p equals to 2, this is at least 6. And this was surprising for many reasons, 2 reasons actually. The first reason is that really this is the first instance where we see that the correspondence we are looking for in between the finitary world and the infinitary world is not as simple as we initially thought. That's the first instance where we see that the infinitary world, the results in the infinitary world might be really more complicated than what you get in the finitary world. So the correspondence is not as simple, and perhaps that's why nobody found it. And the other reason this was interesting is that, so what we did here is to actually use some correspondence that we developed. And originally, we developed some correspondence between the finitary world and the infinitary world in order to use tools from ergodic theory to prove results in additive combinatorics. But here we did the opposite. So here we disproved a result in ergodic theory using the finitary world of combinatorics. So we assumed that the conjecture is true, and we applied some correspondence to turn this problem into a finitary problem. And when we had a finitary problem, to find a counterexample, we needed to solve certain systems of linear equations, which were quite complicated. So we used the computer, and the computer solved those equations. And we tried many examples, and eventually the computer found a system of equations which has a solution. And this gave us a counterexample. And then we used the correspondence again to show that there is also a counterexample in the infinitary world. And I stress this because finding examples into these systems, especially when the degree is very high, is very complicated. And here we didn't need to find such an example. We disproved some finitary result to which we could use the computer, and then deduced that the infinitary result must be incorrect. So we don't really have an example. We just have the existence of an example, just like it's some probabilistic method type argument. Yes, I just want to say that this conjecture was assumed to be true, and many people tried to prove it, and some people even made some progress. So Candela, Gonzalez, Sanchez, and Segedi, they actually showed that the high characteristic case works for 2 more cases. And according to their result, there is no counterexample up to Z3. And we proved that there is a counterexample in Z5, but we don't know what happens in Z4. So there could be a simpler counterexample. And also now we need a new conjecture for this constant. So we know that CK is not K. For instance, in this case, it's at least 6, but we don't know what it should be in general. So let me just put everything into a table. So we talked about the cyclic case, which in the finitary case settings is Z mod NZ, and the obstructions were nil sequences. And the infinitary settings, it was Z, and the obstructions were nil systems. Even so, we didn't know how to prove one using the other. And then we had vector spaces, where we had 2 cases. One is high characteristics, where the results were the same. Both needed polynomials of degree k. And we had general vector spaces, where in the finitary settings, you just needed polynomials of degree k, but in the infinitary settings, you may have, you definitely need polynomials of higher degree. But then the question is, what should happen in general? What should happen when you take any sequence, or even a sequence which contains all of the finite abelian groups with no additional assumptions, no assumptions of cyclic or vector space? And then one can think and see that, well, in the cyclic case, abstractions are nil sequences, which are bracket polynomials. And in the vector space case, abstractions are polynomials. But polynomials are subsets of those nil sequences. And so perhaps nil sequences are abstraction to uniformity in general. But then what should be the version, the infinite version of a general finite abelian group? Perhaps a general countable abelian group. But then if you want to study a general countable abelian group, it suffices to study this group, Z omega. And the Z omega is the infinite direct sum of Z. And the reason why this should be sufficient is that any countable abelian group is a quotient of Z omega. So Z omega is the largest countable abelian group, and you can lift any gamma action to a Z omega action. So this table summarizes our project. So our goal is to generalize Host-Kra theory to arbitrary countable abelian groups, generalize inverse theorems to arbitrary finite abelian groups, and to find ergodic theoretical proof to the inverse theorem to the combinatorial inverse theorem for the Gowers norms. And I want to show you some instances where we managed to do it. So I want to tell you about the result in ergodic theory, which generalized in some special case, the Host-Kra theory. So now we study an arbitrary system, so Z omega system, and we look at the very first non-trivial factor. So Z0 is always a point. Z1 is this rotational compact abelian group. That's the first non-trivial system. And we prove that it is an inverse limit of two-step nilpotent translational systems. So Host and Kra had these nil systems. We needed something more general. A nilpotent translational system looks like a nil system, where the only difference is that this group N is not necessarily a Lie group. So this is not necessarily a manifold. But N is still a two-step nilpotent locally compact group. So we still have the nilpotent structure. A lambda is, as usual, is a discrete co-compact subgroup. Nu is some normalized probability measure invariant to N. And the action is, so an action, a Z omega action means that you have countably many translations and they all commute. And from this ergodic theoretical structure, we managed to give an ergodic theoretical proof for the inverse theorem for the U3 G norm for an arbitrary finite abelian group G. So this was the first instance where we found ergodic theoretical proofs for many inverse theorems results, but it only worked up to U3. If we could somehow generalize this ergodic theoretical structure to arbitrary K, then this would imply a general inverse theorem for arbitrary K, and we would complete the whole picture. But unfortunately, it doesn't seem to be true. The obvious generalization of this to arbitrary K seems to be false. And the reason is that the use of inverse limits becomes weaker as K becomes higher when you have a non-finitely generated group action. So what we can try to do is to see if these inverse limits are even necessary. And unfortunately, they are. So there is an example of Rudolph, even in the case of Z systems. So in Z systems, we know that those factors are inverse limit of nil systems. And Rudolph constructed an inverse limit of Heisenberg systems. So you take the Heisenberg system, always the same action, but you quotient by different groups. So if you quotient by these groups, you always multiply by 2, only 2 out of the 3 coordinates, then you get an example of a system which is an inverse limit of nil systems. It can be approximated by nice systems, but it on its own is not a two-step translational system. So it doesn't have an obvious nilpotent structure on its own. It can only be approximated by systems which has nilpotent structure. But you can still get something. So what I showed is, at least again in the same example, at the same k equals to 2, you have the structure of a double coset z omega system. I won't define it, I'll just show you what happens in the Rudolph example. So in the Rudolph example, it turns out that you can extend the Heisenberg group by adding the two adic integers. And then this two-step translational system extends the Heisenberg example. So any system of order 2, from Host-Kra, it's an inverse limit of nil systems. And from this work, it's a factor of a translational system. And if you want to get the system itself, you have to quotient from the other side by another group. So we have a different structure, an exact structure. So you don't use inverse limits. And in this particular case, k looks like this. You need to divide all of these divisions by 2. So you can get a different structure that doesn't use inverse limits. And we conjecture that this different structure is general. And I remind you that, so if you apply some correspondence naively, this should indicate that perhaps the obstruction to uniformity in the finitary settings are not nil sequences, but some double coset nil sequences. But then I remind you that we already saw an instance where the results in ergodic theory are more complicated than the results in additive combinatorics. So it could be that in ergodic theory, we have to use these double cosets, but still in additive combinatorics, nil sequences are going to be sufficient. So I want to show you many cases in which we develop this double coset structure and still manage to prove the conjecture about the indefinitary case. So one case is arbitrary systems, but with some technical assumption that the system is totally disconnected, which I will not define. But I will tell you that the system is automatically totally disconnected if the z omega action factors through an action of a group of bounded torsion. So it's automatically applicable to, say, FP omega system or Z mod 4Z omega system. So if your action is originally a function of a bounded torsion group, then this is automatically applicable. And then you have the double coset structure. Specifically for FP omega, we proved some version of the Bergerson-Tau-Ziegler conjecture. So we know that the Bergerson-Tau-Ziegler conjecture is false, but if you allow one to pass to an extension, then it's no longer false. So X is a factor of a larger system where the conjecture is true. So the conjecture is not completely false. On an extension, it is true. And using that, we gave an inverse theorem for the Gowers norms for finite abelian groups of bounded torsion, in particular for vector spaces over finite fields. So this is the first ergodic theoretical proof that includes also all the cases of small characteristic. Another case which we did is the case of connected systems. Again, another technical assumption, which is automatic if you have a Q system or a Q omega system. And again, we proved that for these systems, you have the double coset structure. And from this, we gave an ergodic theoretical proof for the inverse theorem for cyclic groups. So it's quite interesting that we actually show that the right infinite version of Z mod NZ is not Z, but Q to the omega. This is the one which gives us an ergodic theoretical proof for the inverse theorem in the finitary settings. Actually, we get a bit more, and with this I will finish. A family, we get an inverse theorem for a bit larger family called approximately torsion-free. This is any family in which, for any prime, there are at most finitely many elements in the family whose order divides P. So example would be Z mod PNZ, where Pn is the nth prime. This is equivalent to the cyclic inverse for cyclic groups, but you can also take this family. So Z mod PNZ to the n, it's no longer a cyclic group, but the results applies. And we actually proved something even more interesting, that you can have an inverse theorem for a direct sum of a family with which is approximately torsion-free, and those vector spaces of over finite fields. You can take as many as you want. So we glue together the two inverse theorems that we already know into one using these direct sums. And yeah, so we just want to improve it a bit by showing that you can replace those vector spaces with an arbitrary group of bounded torsion. And that's it. Any questions?
Thanks a lot. Thank you very much, all. And indeed, questions, comments? I have a small question. You mentioned that near the end that you have a result for U3 for the
yes.
And just to put it on the same level, does that is that related to sequences of length 3 or length 2?
Yeah, no. So it's related to sequences of length 4. So somehow for length 3, you can only use Fourier analysis, and you can do it in general. So length 3 is still the easy case. So originally, the proof of seminority theorem, it started with the Roth theorem. And Roth theorem is the same as Semiramis theorem, but for arithmetic progressions of length 3. And this just uses Fourier analysis, and the proof is like 2 pages, something very, very short. And for a lot of time, it was very, very complicated to generalize Roth theorem to general sequences. And the first one so the first one was semi-ready, but the first one to generalize a Roth argument was Gowers.
Thank you. More questions?
I can't hear you if anyone is talking.
You can unmute if you want to ask. And if not, let us thank the speaker again. Thank you very much.
Thank you very much.
Nice talk.
Thank you.
Okay.